So this is the beginning of section 7.2, actually, where we're going to discuss what we call the washer method. And the washer method is really similar to the disk method. The only difference is instead of being a solid cylindrical disk, it's a cylindrical disk that has a hole drilled out of it. And we'll talk about graphically what causes there to be a hole in it versus being solid. But I'm just giving this thing a little bit of dimension here so you can actually kind of see it as a washer, kind of like the washer game. And what it involves really is just finding the volume of one of those, and it's really just the volume of a cylinder. And remember, the volume of a cylinder from geometry class is pi r squared h. The only difference is we have to do the whole thing and then subtract out that inner hole that's in there. So if I were to kind of take this and piece it apart, what I really would do to find the volume of one of those washers is I do pi times the larger radius squared, give it some depth with the height. That will give me the volume of as if it were completely and entirely solid. But I'm going to drill that hole out by doing pi times the inner radius, which we call smaller r, times the height. The difference is in calculus, this height is approaching zero basically as we make an infinite amount of washers, and we call that dx. And I've really got a pi that I'm going to factor out of the front, and the height, which is really dx, that I factor out of the back. And what that will give me then is the volume of one washer. So we have what's called horizontal axis rotation, which means we revolve it this way across some horizontal line. So I'm going to draw my favorite function here, the square root function, and I'm going to shade it in. And I'm going to say, suppose we're revolving it horizontally about this line down here. Maybe it's y equals -1 or y equals -2. So you've got a picture whipping that thing around. And what it's going to do is it's going to create a solid. What would that solid look like? Well, it would have this, and then it would have this, and it would have a circular basis, and it would have an empty hole in the middle. And that's what it would make. It'd be kind of like a vase that you could put stuff in this time because we have a hole drilled out. Well, when I slice this, like I'm slicing a block of cheese, every slice is what we'd call a washer. And so what I've got on my picture here is we always draw what we call a representative rectangle that's perpendicular to the axis of rotation. But for a washer, it doesn't butt up against its axis of rotation. You can kind of think of that as like a nunchuck, and it's got that solid piece, but then that chain, and that chain doesn't contribute to the volume as you whip it around. So you've got a picture whipping this solid rectangle around that line down there. And what gets created cross-sectionally is, so I shade kind of off the front side to give it a little depth, and then I shade off the back side here to give it a little depth. And this would be kind of like if I were to slice that and serve it up for lunch, you'd each get one kind of cylindrical washer. It'd have a hole in it. And if I were to graphically do this, it has that axis going right through it. If I were to find the volume of that one disk, maybe it would look like this. It would be pi r squared h minus pi r squared h. It'd have that hole drilled out. That would be one cross section. Well, what we're going to do is we're going to do all of them. Because if I kind of picture whipping that around and doing an infinite amount of them, where dx right here, the differential approaches zero, what I really have is an integration process. So to find the volume of that entire solid, I would add up all the washers from A to B, whatever I'm integrating. The pi can come out front because constants can come out front of integration. And then I'd have the big radius squared minus the little radius squared. That gives me, drilling out that hole in it, and depth with dx. So this is the formula, but I like to show you where it comes from, because if I just give it to you, and some books will have that the radius is a function of x, so it might say r of x squared. And that's what we get when we do horizontal rotation. When we rotate vertically, So I'm going to take my favorite square root function again. Again, at any time you need to pause this to catch up. I'm going kind of fast because if I make the videos much more than 25 minutes, they have a hard time uploading. So it goes a little faster in the video than it does in class. But let's pretend we're whipping this bad boy around the y-axis. Well, what would that make? Let's pretend I do it. I'm going to draw it. It would make this. It'd kind of have a circle on the bottom and a little circle on the top, and this would be colored in over here, and you can kind of picture that three-dimensional solid that would be created there. And I'm going to find the volume of that. And in order to do that, I draw a representative rectangle that goes perpendicular to the axis of rotation. But there's a gap here, so there's a little piece of like dental floss or a chain or something that's not contributing to the volume. But when I whip that blue thing around this axis, right, it's going to make what we call, oops, that's not a very good thing, a washer. It'll look like this if I blow it up. It'll have some depth off the front, some depth off the back, it'll have an axis stabbing it through the center, and I've got to find the volume of it. Well, same concept. I would have here on here, that's my big R, that's my little r. On here, they're going horizontally, so that's big R and that's little r. So I would do pi big R squared h, but now I'm a differential. Oops, sorry, my differential is y axis parallel. So my height is dy minus pi baby r squared dy. It's just cylindrical minus a cylinder, really. In calculus, but what we do is we're going to add them all up, an infinite amount of them, to create the entire solid. So what you're doing is you're picturing, again, not me whipping one of them, but every single one around here. And I'm going to do an infinite amount, and I'm going to fill it all the way up to the top is what I'm going to do. So what I end up getting is my pi comes out front. My r squared is actually now a function of y because we can't have a variable match. And it's a dy differential. And my limits run up the y-axis. So sometimes you'll kind of think of this as being f of a, f of b. So now let's apply this. I wanted you to see where the formula came from before we go use it. So here's the formula laid out in full, but one thing to notice, the tricky part is finding big R and little r. So big R is not only the larger one, but kind of keep in mind it's the distance from the axis of rotation. Whatever that might be, it's not always the x or y axis. Sometimes we revolve it around like the line y equals 5 or something. But you go from the axis of rotation to the outer edge of the curve. For little r, we go from the axis of rotation to the inner edge of the curve. So let's discuss the difference visually between what we call discs and what we call washers. So you'll notice right here I've got my curve represented by 9 minus x squared. It's a quarter of a circle up here. And I am whipping that sucker around the x-axis. So I draw my rectangle perpendicular to the axis, and it butts up right against it, so there won't be any hole created. This thing is going to, when I whip it around, going to give me, when I whip that around this axis, it's going to give me a very solid, right, figure with no hole drilled out of it. So this is what I would call a disk problem. My differential is on the x-axis, so it's a disk dx. So when I set it up, what I'm going to do is add up all of those disks that would be created, all these solid disks that get created when I whip this around. They look like pennies. We're going to add them all up from 0 to 3. Each one of them is a cylinder. Cylinders are pi r squared h. Well, what is my radius? It's from the axis of rotation to the outer edge of the curve. So big R would be however high up that is. Well, each one of these points is x root 9 minus x squared. So R is actually just the height of the function, which is the square root of 9 minus x squared. So I've got pi integrating from 0 to 3, r squared dx. And you might think, well, where's little r? Little r is actually 0 for a disk because there's no inner radius, which becomes pi times the integral from 0 to 3, 9 minus x squared dx, because the root undoes the squaring. So that could be done by hand or on a calculator depending on what you were told to do. So let's take a look at this one. Again, I'm whipping around the x-axis. My rectangle is drawn perpendicular to the axis of symmetry, but there is a gap, which means this is going to create a washer when it whips around. It's going to have a hole in it. So what I do, gotta make an ice washer. There we go, ice washer. There we go. So what I do is I take a look and notice that I've got a dx problem. It is a washer problem. It needs to get integrated. All right, my formula is pi r squared h minus pi r squared h. Well, what is big R here? The big radius is from the axis to the outer edge of the curve. It's from here up to here. So it's the y value on this curve, which is 4 minus x squared over 4, as defined up here. Baby r is from the axis of rotation to the inner edge. It's this on your washer. And that is constantly 2 for this. So when I set it up, I say I need to subtract the little cylinder from the big cylinder. So I do pi r squared minus r squared h. And my limits are running along the x-axis. Now here's a clever trick. Instead of running from -3 to 3, because if you have to integrate by hand, that's much more difficult than going from 0 to 3. So how about we just integrate this half and double the whole thing? Let's go set that up. We'd have 2 pi integral from 0 to 3 r squared, so it'd be 4 minus x to the 4th over 4 squared minus baby r squared dx. And I'm going to go dot, 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 and we'd probably math 9 that one, or integrate it by hand if we had to. So here's another example. We've got the cosine graph and we've got the sine graph intersecting right here. And we're whipping it around the x-axis again to form this solid. Now, when I draw my representative rectangle here, I see that I've got, and it goes perpendicular to the axis of rotation, I've got a dx problem, but I've got a little gap here. So this would be what I call a dx washer problem. So what I need is capital R, axis to the outer edge, and baby r, axis to the inner edge. Axis to the outer edge is the y value on the top function. The top function is cosine because cosine 0 is 1, sine 0 is 0. So big R is cosine x, whereas little r is axis to the inner edge, which would be sine x. So to get the volume of this entire solid, I would do pi times the integral from 0 to here. Now be careful that you don't think that's 1. That's where sine and cosine intersect. So we're not doing a 1, 2, 3, 4, 5, 6 grid. You can see down here the window. Our input here is we are kind of like zoom trigging it. We are going by pi over 4s. And sine of pi over 4 and cosine pi over 4 are both root 2 over 2. That's where the two functions intersect. So I do pi times big R squared minus little r squared dx. And what I would do is take out your calculator and run that through with your Math 9 just to see what you get. And I believe you end up getting 1.57 or so. I'm not positive, but I think. So here's what's really important to consider with these. You must have a good picture. If you can draw it, you can do it. Your rectangle always goes perpendicular to the axis of rotation. Identify axis to outer, axis to inner. Make sure when you write those that you don't write it as r minus r quantity squared. It's pi r squared h minus pi r squared h, where pi gets factored out the front, h is really dx or dy, which gets factored out the back, and for integration, constants come out front. All right, so let's go do a few examples. I don't know how many I'll get in, but we'll go do a couple. So the first thing is draw a great picture. And the picture for all of these is the same. We're going to be doing the line y equals x, and the curve y equals x squared. And we're going to find region R is enclosed by both of them. So region R is like this banana peel that I'm going to shade in. And again, pause at any time to catch up with my sketches. I'm going kind of fast due to time restrictions on the video. All right, so let's go take a look. What am I whipping that sucker around? I'm whipping it around the x-axis. So my first thing is to draw my representative rectangle perpendicular to the axis of rotation, noting I have a dx problem and it's a washer problem because of this little gap with the x-axis. If I were to draw what the entire solid looked like three-dimensionally, it would be that banana thing on the top. I hate shading on this stupid smartboard. And then it would have the banana thing on the bottom. Oh, that's not very good. Sorry. My eraser's being extra big too. So then it would have the banana thing on the bottom, right? It's going to kind of come in like that. And then it'd be circular here, and it would be kind of a tipped over. I don't know, it almost looks like a Hershey Kiss with a hole drilled out of it. So when I do my cross sections, you'll notice they're all going to be washers. And here's my axis stabbing through the center of it. So I need capital R. Capital R is from the axis to the outer edge of the region. So capital R here is from this axis of rotation to the outer edge. Well, that goes up to the point labeled x, comma, x. So in terms of x, because this is a dx problem, that height, capital R would just be x. Well, baby r is from the axis to the inner edge of the curve. Well, this is the point x, comma, x squared. So that's x squared from the axis up to that point in the curve. So when I set it up, and I don't memorize formulas, I just get it. I'm doing pi r squared h minus pi baby r squared h. And I'm going to do that along the x-axis. So I'm going to go from 0 to 1. So let's go look at how we do the letter C. I'm going to skip B here for a second. Let's go do letter C. We're going to whip that sucker around a different thing, but it's the same shape, so let's just draw it. It was that banana peel shape created by, and I'm not going to shade it in. And we're whipping it about the line y equals 2, which is up here. So this is y equals 2. So I'm going to be rotating the up and around here, creating a solid. Notice that the solid would have this kind of base here, and you can kind of picture what it's going to look like. It's going to have that banana peel over there, and it'll be very pretty. But my goal is, again, to notice that when I draw my rectangle perpendicular to the axis of rotation, and I put it on a string attached to the axis of rotation, that I've got a huge hole in there, and this is definitely washer, and it's still dx. Here's my problem. I'm going to go erase that. R can be a little tricky, so you got to, but again, if you can draw it and visualize it, you can do it. Big R is from the axis of rotation. That's up here to here. That's big R. That would be the radius of one cylindrical washer on the whole big thing. And then we're going to drill that hole out in just a moment. But big R goes to this curve. Remember, this curve is x comma x squared. However, the x squared represents, so it's x over and x squared up. Well, I don't want that. I want the rest of this. So it becomes 1 minus that gap with the x-axis. Likewise, baby r is from the axis to the inner edge of the curve. You can kind of picture it on the big solid, what little r would be. It's the radius of that hole that's drilled out, which varies as you move along here. However, this is at the point x comma x. Well, I want this, so I do 1 minus it. So now when I set this sucker up, this is what I've got. I've got the volume is equal to pi times the integral, and we're integrating along the x-axis from 0 up to 1 of big R squared minus little r squared and I need my dx on there, and I would be done. All right, so let's look at letter D. I've got 6 minutes here, so I'm not quite sure how far I'm going to get. But letter D, again, we just have to have a little bit more thought. We still got that banana peel. Let's go draw it on there. Intersecting in that corner there at 1, 1. All right, so for letter D, I'm revolving it around y equals -5. So I'm pulling this farther away from its axis of rotation just creates a bigger hole in the solid. It makes it more fragile and breakable because I've got this big, you can picture what that would make. It'd hold a lot more water, but the volume of the actual solid is not very great. So what I need to do now, again, is draw my little rectangle here perpendicular to the axis of rotation, connect it with that invisible piece of dental floss, note that it's a dx problem, start whipping that nunchuck around, and create my solid. And I'm going to whip an infinite amount of them around, each hardly any thickness, all the way over. So I'm going to integrate from 0 to 1, pi out front. Now be careful with our capital R again. Capital R is from the axis of rotation to the outer edge of the curve. Well, it's 5 just to get to the x-axis, plus I have to go all the way up here, which is the point x comma x. So it becomes 5 plus x. Baby R is from the axis of rotation to the inner edge of the curve. Well, I've got 5 just to get to the x-axis, plus I have to go up to x comma x squared. So it becomes 5 plus x squared. So when I integrate, I get big R squared minus little r squared dx. And if I had to do it by hand, I'd FOIL, combine like terms, use my antiderivative power rule, or by calculator, I would math 9. So the last one I think I'm going to do in this video for you. Let's head on over here, and then after this one you should work on worksheet 7-2. All right, so for this one right here, same banana peel. So go ahead and shade it in. Rotate it about the line x equals, I forgot if it was -1 or -2. Let me go take a peek here. Rotating it around the line x equals -1. Good thing I looked because I was going to do it about -2. So I'm going to whip that banana. Whoopsie. Let's be a little bit, I don't want to erase that. So I'm going to whip it around this line. Again, I draw my representative rectangle perpendicular to the axis of rotation. I connect it with its little invisible piece of string. I note that my differential is now along the y-axis, and I'm going to be having my washers look like this. And you can picture what that would make. It would put that other piece here, it'd have circle on the top, and I would get this washer going like this with a big hole in the middle of it. All right, and if I could do an infinite amount of them and spin them around all the way up the y-axis here, I would get the volume of the solid. The volume of the solid is pi, integrating up the y-axis from 0 up to 1, big R squared, and this is a dy problem. So everything in terms of y now. So big R goes from the axis of rotation to the outer edge of the curve. And yes, that's the point x comma x. The problem is I can't use it as such. So sorry, my eraser's been really messed up since I had my smartboard fixed. But right here is the point x comma x squared. Well, great, but the issue is I can't, yes, it's x from here to here, my big R, but I need to have it in terms of y. So what we do is we write it as y root y. Instead, we have y be the independent variable for the function. So this big R is the square root of y squared. Little r is from the axis to the inner edge of the curve, but again, it has to be in terms of y, so you'd have another y. You would then integrate that by hand or math 9 it, and I am going to be done. Peace out, Aaron.